This presentation discusses dimension reduction methods. The objectives are to describe the bias regression techniques that can be used, and that will make more sense as we go through it. Explain the differences between principal components regression and partial least squared regression, and then describe the partial least squared algorithm. With respect for regression with multidimensional data, there are many ways to take advantage of the dimension reduction techniques in regression type models. So some examples are going to be the discriminant function analysis, which we have another video about. But this presentation will include a discussion about principal component regression and partial least squared regression, also referred to as PLS, of which are both a part of the family of structural equation modeling techniques, which is called SEM, and there are many different types. These are just going to be two examples of structural equation modeling techniques, and there are many, many more. So this discussion will be focusing on principal component regression as well as partial least squared regression. And once again, in another video, we have discriminant function analysis. Multivariate regression finds a linear combination of predictors that maximally predicts a linear combination of responses. Multivariate analysis of variance, also called MANOVA, finds a linear combination of responses that maximizes the distance between group means. MANOVA can also handle polynomial effects, categorical variables such as two-way interactions, and these are going to be considered unbiased methods. Let's talk about some dimension reduction regression models. One is principal components regression. So principal components maximizes the explained variance in the predicted variables. Partial least squares regression uses the method for alternating least squares to extract the principal components and find the variable weights while considering the associations between the partial responses and the predictor data. Partial least squares is used exclusively for predictive and descriptive modeling, and there are not any inferential hypothesis tests that are performed when you execute a partial least squares regression. These are biased methods, but they have reduced prediction variance over ordinary least squares regression, and sometimes also probably a reduced parameter estimate variance too. So let's talk about what's going on in terms of regression. So when you're using principal components analysis, we're using projection. So as a reminder, here we have some data points, and you're looking at the line that catches most of the variance, which will be your first principal component. And then you're looking at smushing it together to project it onto that red line. And then typically you're going to rotate that factor or principal component as you use your regression. So what's the deal with projection? Well, data can be rotated, scaled, and translated without changing the underlying relationship of the data. So this means that you're allowed to look at the data from whatever angle makes your life easier. And in our case, we'll be able to use principal components for regression. So what we're doing is we're transforming the data, but before performing a regression. So instead of using each of our x variables, x being each of our predictor variables that you have, instead of using 5 predictor variables, maybe we only want to use 2 principal components as our predictors in our regression. Why would we want to do that? So perhaps there's multicollinearity between our variables, and by using principal components which are orthogonal to each other, which means they are independent of each other, therefore they will not exhibit any of our multicollinearity issues. Also, with all things being equal, if we have fewer predictors, it's going to lead to a simpler model, and that would be another reason why we might want to use principal component regression. So instead of finding the beta parameters that minimizes the sum of squared errors, we're trying to find these beta coefficients, and so we're trying to minimize the sum of squared errors that way. And what we can do is find a regression model that minimizes the sum of the squared error, but instead of using the x variables, we are using the principal components instead of those underlying predictor variables. So what's the difference between PCR and PLS? Principal component regression models the response by finding new dimensions in the predictors that explain the variability in the predictors. And PCA explains maximum variability in the predictors. This regression maximizes the correlation between the response and the principal components. On the other hand, partial least squared regression models the responses by explaining the variability in both the responses and the predictors while maximizing the covariance between the responses, and the predictors. So again, the key idea is that when we take into consideration both the X and the Y, whereas PCR approach is only considering the variability within your X values. PLS regression considers two sets of variables like X and Y, and the components are extracted one at a time. The operations for X and Y are carried out individually, generating scores based on X and scores based on Y. Again, it considers both your X and your Y, and subsequent components are extracted with regard to association with the variables in the other set. And one goal that we will have is to determine the best number of components to retain for the analysis. Ultimately, when we are trying to use the regression for prediction, the partial least squares regression is going to be more effective because this is taking into consideration the Y component of the Y responses as well. So let's take a step back here and look again. Why do we pick this line here, and why are we looking at principal components? So again, as we've discussed before during principal component discussion, this line represents the line that captures the majority of the variance within the data set, or the highest percentage of the variance. The first principal component will capture the most variance of all the other principal components, and the second one will do the second most, and so forth. And then typically what you're going to do is then you're going to rotate that principal component, and you end up with looking at the principal component that we see here at the bottom. And so this one at the bottom is the one that's going to be capturing the majority of your variance. There are two algorithms that are used in practice. One is NIPALS, which stands for nonlinear iterative partial least squares. It is more the traditional algorithm, and it is not designed to optimize an objective function. There's statistically inspired modification of PLS, simples, and it's designed to optimize a specific objective function. But when you have only one response, then NIPALS and simples are going to be equivalent. So one would be looking at the principal components regression, and the other one would be looking at the partial least squares regression.